everybody. Today is our last session of the Asia Pacific Conference of Young Scientists, APCYS 2021. We have shared an incredible week with all of you, haven't we? To start today's activities, we are very honored to welcome Mr. Alfredo Manriquez, who will provide us with a conference titled Quasars, a case study for the scientific method. To all the audience, remember that at the end of the conference, you can participate in the question and answer section. Now, let me introduce to you Mr. Alfredo Manriquez. Mr. Manriquez has a bachelor's degree in physics and a master's degree in astrophysics by the Autonomous National University of Mexico, UNAM. He also has a doctorate studies at the Institute of Radio Astronomy and Astrophysics with a thesis focusing on galactic hydrodynamics. He has been working as a scientific consultant since 2019, when he founded Nostro Data alongside Mr. Gustavo Muñoz and Mrs. Rocio Bermudez, a company focused on big data and analytics. Alongside these activities, he has more than 20 years of experience as a public speaker for science outreach and astronomy workshops under the tutelage of Antonio Sánchez Ibarra, National Prize for Scientific Outreach 2001. Mr. Alfredo is an avid promoter of science and critical thinking as a way to better solve local problems in his community, and likes to share these with his students and the general public. Welcome, Mr. Manriquez. The mic is yours.
Thank you very much. Well, I would like to start by thanking all the staff and the organizers for the event. Gracias a todos por tenerme aquí. This talk that I will be giving today, it's a very personal one because I would like to start with a little bit of story of myself. When I was young, I started working coming to the university to the area of astronomy here at Unison, the local university here in the state of Sonora. And I met Mr. Antonio Sánchez Ibarra. When I was young, about 13 or 14 years old, I remember that there were lots of things in astronomy that were not as readily available as they are today. Usually when someone wants to learn something, today you just have to go to the internet. So today I will talk a little bit about quasars. It's very interesting because when I was young, things were difficult to find. Learning used to be very slow, not difficult, but slow. What do I mean by that? If you wanted to look for something that was like in the avant-garde of science, you had to go to research papers, you had to go to research centers, to universities to find about those topics. Or you have to buy magazines or other kind of published materials in order to get those products. Now we have Wikipedia. So the only thing that you have to do to learn something new is go to Wikipedia and look for this new information. Back then, the things were not so easy. So with quasars, I remember that I was having a kind of a problem figuring out what were quasars. And when I started studying physics and astrophysics, I learned a lot about quasars, and I was able to answer the questions that I had when I was young. And this process was very revealing to me, because as I was studying sciences, I was learning something about myself that I was trying to figure out since I was young. And in particular, quasars were these weird things that everyone was talking about during the 90s and early 2000s. And eventually we found out what they were. And this talk is about, the story of how we found out what quasars were. So I would like to start first by showing you if this works. I don't know why this stopped working. So I'm having a technical problem here. Sorry. I'm so sorry. I'm having a technical difficulty with the presentation. Okay. Oh. Okay, it looks like it's ready. Okay. Yeah, so quasars were discovered in 1964. Here we have the abstract for, well, the first paragraph of the abstract for the paper where 2 quasars were first reported. The word quasar means a quasi-stellar radio source. It means that when you look at a quasar, you look at something that looks like a star, but it's not really a star. Here in the image, we have a couple of points, of bright points that look like stars, but they are not really stars because they are really, really far. How do we know that the quasars are really far? Well, here we have in the first image the Einstein cross in the constellation of Pegasus. It was discovered in 1985. And when astronomers first look at them, you can see that we have 4 bright dots there that look like stars, but they are behaving in a weird way. Alongside these objects, we started to find another star-like objects around the skies since 1964. And with the use of this Hubble Space Telescope, now we have a very good image of these objects. Here we have another quasar, for example, where we can see like these 2 bright dots in the image. And here is another. In this third one, I want to emphasize the fact that alongside this bright spot in the center, that it's the quasar, we have another objects around it. And if you pay close attention to these objects, you can find out that they are galaxies. Quasars, the main characteristic of quasars is that they are really, really, really far. They look like stars, but they are maybe millions of light years away from us. And they are at the distance of distant galaxies. So in this image, we are looking at a quasar in the center and a lot of galaxies surrounding it. The object that I'm showing you now, it's another quasar, and here we have another couple of galaxies surrounding the quasar. And if you pay close attention, what we are looking at, it's a bright point surrounded by galaxies. And this was very puzzling. In the paper published in the Astrophysical Journal, in 1964, they studied 2 objects in particular. One is named 3C48, and the other one is named 3C273. We are going to be visiting these 2 objects a little bit later, but the one that I will be focusing on will be 3C273. If you pay close attention to the abstract, you will see that alongside the title, that it's the first time that we see the definition of a quasar, we see at the end of the first paragraph something that I was very interested on. I found that very funny that we have a paper of about 40 pages long. It's 40 pages of scientific data of astronomy and astrophysics research. And in the abstract, they say, we basically don't have any idea what we are looking at. It was the first time that I found out that science was not this monolithic thing with all the answers. The professors and astronomers that were working with quasars, the first one that that look at quasar, basically they say, well, we have these bright spots surrounded by galaxies. It's really, really far, really, really bright, and we basically don't know what it is. So it was very revealing to me because I was trying to figure out what quasars were, looking at their first paper published in 1964 about quasars, and they did not have any idea what quasars were. So when I started looking at the papers and the research done around quasars, I realized that the story of quasars was very interesting because it showed how the scientific method worked. So when they were discovered, scientists had no idea what was going on with them. And during the next years, we started to figure out what they were by using scientific data and astronomy pictures. So that's what I'm going to talk about next. So in the scientific journal that I'm having trouble again changing, they say that they don't have any idea what quasars are. In this paper, they showed a couple of images that they took with a couple of optical telescopes where the quasars are shown in these pictures. First, we have the first quasar here, 3C48, and as you can see, it's basically another star among many other stars. It's just a a dot in the image, and it's not really very different from the other ones. Besides that, the fact that they could measure the distance to this object, and the distance was extremely large. I think I have control now. The other object that I studied, the 3C273, was something very similar. We have the bright spot here in the center of the images. And if we look at this object with modern technology, for example, with the Hubble Space Telescope, we see that the image becomes clearer, but we don't have that much information about it. Besides the fact that we have this weird filament on the side of the image. So what's a quasar? We have a couple of galaxies there, and besides the color, the image in color, we don't have that much more information with the Hubble Space Telescope. So what can we use to look at quasars? Well, the conclusions of the article were very revealing because they gave us clue about what to look for when we were studying quasars. First, the conclusions were that they are very far. How do we know that they are far? Well, if you take, for example, a redshift measurement for the object, you can measure the distance to this object by using the speed in which the object is moving away from us. It's called the Hubble law, well, the Hubble-Lemaitre law, since a couple of years ago. Besides the distance, they are really, really massive. We can measure the way in which matter moves around these objects and measure the mass that they have. They should have a gaseous shell. What do I mean by that? When you measure the light of an object, you can check how this light is being produced. If the light is being produced in a gaseous shell, you can measure the movement towards you and the movement away from you by using the Doppler effect. So if you can measure these two movements, usually it means that you have a part of the object that is moving towards you because you have a shell expanding, and one part of the shell is moving towards you and the other one is moving away from you. That is something very simple to do by using the Doppler effect. And besides these three characteristics, they should be compact objects because we couldn't see many things around them. And finally, the last conclusion is that they are really, really, really bright, so they are extremely shiny. And, well, how can we know more about these objects? If they are really far, usually astronomers use something called radio waves. Radio is the way in which communicate, or we used to communicate through radio, it's still used, and through the radio waves, it's the way in which we can communicate with other objects, for example, the television signals or other kinds of devices that we use today use radio waves. But in astronomy, radio is like light. We can use basically radio waves the same way in which we use visible light. This is very interesting because we have a problem with radio waves. If we try to use an optical telescope, we only need a mirror to reflect light towards an eyepiece. In the case of radio waves, we can see radio waves with our eyes. So what we use to look at radio waves were big antennas. And these antennas have to need a couple of detectors in the focus point of the antenna. In order to see clearly with radio waves, you need big antennas. And for example, we have here an image that looks like a salamander. The way in which this image is shaped looks like an animal with thermal vision, but in fact, we are looking at Jupiter in radio waves. On one side of the image, we have Jupiter in visible light, and in the other side of the image, we have Jupiter in radio waves. The fact that we can see this bright band in the middle is because a moon orbiting around Jupiter is expelling a lot of gas that interacts with the strong magnetic field of Jupiter, and this produces this extremely bright radiation in this spectrum. So we know how to use radio waves to look far, but if you look at the image of Jupiter, it's not very sharp. We cannot discern the details that we can look at in the visible spectrum. So what can we do to look far and sharp? Well, here we have a couple of telescopes called the Keck telescopes in Hawaii. We have an instrument called Interferometry that is used in astronomy to look at very far objects with a very sharp definition. These objects were constructed in the late 70s, and this was available at the time because we developed the computer capacity to analyze the images produced by these antennas. But the way in which interferometers work was known for 100 years before we started building big interferometers here on Earth. But the way in which we have to process the light and process the information was not very easily back in the day in the 1800s. We needed computers in order to really understand what was going on with the light and with the information produced by interferometers. So when we had computers around the 1970s, we could take all this information and put it together by using computers, and we could produce really sharp images for very far objects. And this interferometer in particular that I'm showing on the image is a VLA. It's a very kind of old interferometer, but some of the information that I will be talking about is taken with an array similar to this one. The VLA has 27 antennas that can move alongside some like rails, train rails that move the antennas for different configurations. Each antenna has a parabolic dish of 25 meters wide. when you take all the 27 antennas together, you can produce an image that is the equivalent of having an antenna of the width of the farthest two antennas that you have. And on the widest configuration, the VLA has a width of 36 kilometers. So this is the equivalent of having an antenna of a width of 36 kilometers. It's a very big antenna. There has been another couple of experiments and observations taking together observations from different antennas around the world, and essentially you can have an antenna that has the width of the entire world. It's around 2,000 kilometers wide. So if we use these antennas, we can look at really far objects and with really sharp definition. So what can we do with radio? Okay, basically, if the telescope is really wide, we get a sharper image. And if we point these telescopes towards quasars, we can look at them and see how far they are and look at them really, really, really sharp. So the object that I'm showing here, one of the two published on the paper, 3C273, is around 2,000 million light years away. The number seems kind of big, but in reality, it's not that really far. We have seen objects that are farther than this one. And basically, this is one of the closest quasars that we have to Earth. If we look at it with a radio, we can... Okay, I'm having trouble again. If we look at radio, if we use radio waves to look at this, we can look what's going on with this object. And here it is through 3C273 in radio. If you pay close attention to this image, you can see that the object in the center is bright. We can see the point aligned with the bright star that we can see in the visible light. And on the side, we see like this filament that is, well, if we superimpose the radio image with the visible light, one, we can see that we have like this jet that is aligned with the filament that we saw in visual light, in optical light. So if we look at the other one, at the other object, 3C48 in radio, we can see that it has a similar structure as the other one. I took this other image just to compare it with the other ones with the same color palette. So if we put the three images together, we can see that quasars, these two objects that were first reported in 1964, have jets that are visible in different lights. We have visible light, that is the light that we use to look around with our eyes. Radio waves, that are the lights that we use to communicate with television and radio, and X-ray, that are the lights that we use to look if we have a fracture in our bones. X-rays are the most energetic of these kind of lights. On the center, we have visible light. On the high energy spectrum, we have X-rays, and on the low energy spectrum, we have radio. So these objects are radiating in all lights imaginable. We have something in the middle, something on the high energy spectrum, and something on the radio low energy spectrum. So these objects should be extremely bright and extremely active in order to be radiating in all these lights. So what's going on here? If we pay attention to the images, we can see that the position of these clumps of light that are shown on the images differ from image to image. First, we have in the X-rays these clumps on the upper part of the image. On radio, we have the clump on the lower part of the image, and in visible light, we have a couple of clumps, well, alongside all the filament that is on the side of this quasar. So these clumps are produced because there should be gas there. There should be something there that is really, really hot. If the gas is extremely hot, it will radiate in X-rays, and if it's not that hot, it will radiate in radio. The mechanisms in which the light is produced tell us something about the materials and the composition of the gas that is radiating this light. So if these two quasars have jets, the first two quasars that we found, they have these weird structures flaring out from the center star or quasi-star thing that we have in the center. Well, let's look for jets in other objects. We have a couple of other objects in the sky that are called radio galaxies or active galaxies that show jets flaring out from the center of these galaxies. Some of these objects have two jets, and others only have one. This is because of some relativistic effects that show only light going towards us. So if we look at this image here, here are two jets, but if we superimpose the visible light image from this, the image is revealing a galaxy. So jets are basically observed in galaxies, in radio galaxies, and if we look at the stellar light, at the visible light, we can discern a galactic disk, but these disks are not watchable in quasars. So what's going on there? Okay, this image here is a simulation of this very same object, but they superimposed the two jets flaring out from the center of this radio galaxy. The galactic disks are usually dim compared with the brightness of a quasar. So if we expect to watch a galactic disk in the center of a quasar, it probably will be well, obstructed because of the light of the quasar itself, because they are really, really bright. So we have to find a way to dim the light of the quasar in order to find if they have a galactic structure. So let's find if we can do that. If we try to look for a disk in these objects in 3C273, dimming the light will be necessary. So how do we do that? Well, we have an instrument called a coronagraph. These are used with the sun. Basically, they produce an artificial eclipse. How do they work? Well, we just put something in the center of our telescope or of our camera, and if we block the light from the source, we are able to see these structures around the source, in this case, the sun. If you look at the image that I'm showing, we have a couple of images taken from a space telescope called SOHO. It's a Japanese solar telescope. This telescope has a coronagraph in the center of the image, and here is superimposed the image of the sun just to show the scale of our star. In the center we have the sun, and on the outer parts of the image we have these flares that are being produced in the solar corona. The corona is the outermost atmosphere of the sun, and it's really, really hot, but really, really dim. So we have to block the light from the sun in order to watch it. It is usually observed during total solar eclipses. So if you have the opportunity to look at a solar eclipse, well, a total solar eclipse, you can look at the corona. And if you want to know when one is going to be available for you, well, in 2024, we're going to have a very great total solar eclipse here in Mexico. So you might be welcome here to come and visit us to watch one of these events. So if we have this coronagraph to block the light, let's block the light of the quasar. And what happens? Here we have an image taken with the Hubble Space Telescope. They installed a blocker of light on the Hubble Space Telescope, and by using strategies and techniques to analyze the data, we can abstract the light of the quasar itself. So when we block the light of the quasar, we find out that this quasar has a galactic disk, the very same thing that we expected to see from other observations taken for radio galaxies. So what we are looking at is that quasars are basically galaxies that are really, really far, but have something in the center that is producing jets, and they're really bright. So when we started looking at these objects with the Hubble Space Telescope, we started to find out that these quasars had galaxies surrounding them. And if we start to talk about this object, we have to figure out what's going on in the center of these galaxies that is producing this bright light in radio, in X-rays, and in visible light, and it's producing these jets away from the galaxy. And probably some of you already know what's going on in the center. So what do we know so far? So far, we know that quasars are galaxies that are really, really far, that have very bright nuclei emitting in the visible and radio light. And basically, not all quasars